Let's now talk about half-lives of particles. So we've said that unstable nuclei can decay spontaneously. We can work out how likely a nuclei is to decay. The decay is a random process, but it is related. There is a probability for it which is related to the half-life of that particle. So the half-life is the time it takes for half of a sample of an isotope to decay. So if we had a kilogram of an isotope, the time it took for us to have 500 grams of that isotope would be the half-life. It would actually take then the same amount of time for us to have a quarter of a kilogram, and then after the same amount of time again had passed, we would have an eighth of a kilogram of that isotope left. So we actually have a decay graph which looks like this. And so let's have a look now at a simple calculation that we can do using the half-lives to work out how much of a sample is going to be left after a certain amount of time.
So the question is, radon-222 is a commonly occurring isotope in nature. It is present in some houses and is a health risk. It is found that 3.0 times 10 to the 7 radon atoms are present in a room. If the half-life of radon is 3.83 days, how much radon is present after 31 days? So in order to answer this, we need to consider how many half-lives have passed. So number of half-lives, we've got 31 days, and each 3.83 days is a half-life. So this gives us about 8.1, which is approximately 8 half-lives. Now each half-life, half the particles disappear. So the number remaining is the initial number, 3.0 times 10 to the 7. Now if it was one half-life, if we had 3.83 days passed, then we'd times it by a half. But as we've got 8 half-lives, we need to raise this factor of a half to the power of 8. So solving this on the calculator, we end up with approximately 1.2 times 10 to the 5 radon atoms remaining.
Now, one property that we often consider with radioisotopes is the amount of activity, which is the number of disintegrations per unit time. So we can write this activity as delta N over delta T. Now, the amount of activity is related to the number of particles that we have. The more particles, the more that are going to be disintegrating. So we actually have the equation delta N on delta T is equal to minus N times lambda. Now in this equation, N is the number of particles of that isotope, delta N is the change in the number per unit time, delta T is that per unit time, and lambda is what is known as the decay constant. So it's different for different isotopes. And the negative sign is there because the more particles we have, the more decays, and these decays reduce the number of particles that are then present. So let's now have a look at how lambda and the half-life are related.
Okay, so we want a relationship between lambda and the half-life. Okay, so let's start with our equation that the change in the number of particles over a given time interval is equal to minus n times lambda. Now let's consider this for very small changes. So for small changes, we can write dn dt is equal to minus n times lambda. And this is really how we're defining this decay constant, lambda, here.
Okay, so what we're going to do now is try and come up with an expression for what lambda is. So we can write this as dn on n is equal to minus lambda dt. And then let's solve this. Let's integrate both sides. And so when we integrate 1 on n dn, should be the same as 1 on x dx, we end up with log n. And then when we integrate minus lambda dt, we end up with minus lambda t. And then we've got some constant of integration here. Okay, so we've got log n is equal to minus lambda t plus c. So let's get rid of this log. So to get rid of the log, we're going to raise both sides to make both sides the power on the exponent. So when we do e to this and e to this, we end up with n is equal to e to the minus lambda t plus c. And so we can write this as e to the minus lambda t times e to the c. This constant is just some constant we don't know, so we can write this whole thing as a different constant. So we can write this as, say, a e to the minus lambda t. Okay, so we now have our equation n is equal to a e to the minus lambda t. Now, it's standard notation to let the number of particles at t equals 0 be n is equal to n0. So we can substitute this into this expression to find out what our constant a is. So we have at t equals 0, we've got n0 is equal to a e to the minus lambda times 0. Lambda times 0, that's 0, and so we have a e to the 0, which is equal to a, because e to the power of 0 is just 1. So we've got a is equal to n0. So this tells us that our expression for the number of particles n is equal to n0, the particles at time 0, times e to the minus lambda t. Now what we're trying to do is get a relationship between lambda and the half-life of the particles. So we know that when t equals 1 half-life, t1 half, we've got that n is equal to a half n0. That's by definition of what a half-life is. A half-life is when we have half the particles left. So now what we can do is substitute this t and this value of n into our equation here. So we've now got a half n0 is equal to n0 e to the minus lambda t1 half. And now there's an n0 on both sides, so those cancel out. And this tells us that a half is equal to e to the minus lambda t1 half. Now what we're going to do is the opposite to what we did here. We're going to take the log of both sides now to get rid of this exponent. So when we do that, we end up with log of a half is equal to log of e to the minus lambda t1 half. And so we can write this as, this is log of 2 to the power of minus 1. And so we can write this as minus 1 log 2. That's minus 1 times log 2, so i.e. just negative log 2. And then this, we can bring this exponent out the front, is equal to minus lambda t1 half log of e. Now log of e, this is equal to 1. Try it on your calculator if you don't believe me. And so these negatives cancel out here, and what we end up with is log 2 is equal to lambda t1 half. And so this tells us that lambda is equal to log 2 over t1 half. So we've now come up with an expression for how to relate lambda, our decay constant, to our half-life, t1 half. So this is important and useful, but this equation here is especially important and useful, and we'll be using this one going forwards as well.